the length of human pregnancies is from conception to birth varies according to a distribution that is approximately normally distributed with a mean of 266 days and a standard deviation of 16 days. Okay, so what I'm being described here is this is the let's call it the parent population. In other words, population I am sampling from. Let the random variable y measure the length of the pregnancy. Okay, so an all independence means is that when you pick a person, the next one has exactly the same chance of being whatever you want it to be. In this case, what is probably that a randomly chosen hospital record shows the length of the pregnancy lasted longer than 202 days. Now, let's read this really quick. I'm sampling from a distribution that is approximately normal. So as soon as you hear the word approximately normal, this is code word for use a normal distribution. Write the mean here. The mean is 266 days. I'm going to just, y is my variable. I'm challenging myself. I'm trying to use other variables besides x. So again, this is random variable y. I got my standard deviation. And that's going to be 16 days. Great. And now the question is, what's the probability that a randomly chosen hospital record shows that the length of human pregnancy lasted longer than 202? So wait a minute. What's the sample size here? What a random A means singular. It's a singular. Record is notice singular. So what this says is this question does not concern the sampling distribution, because I am not summarizing anything. I'm only choosing one value, and it's kind of hard to summarize a single value. So my sample size is just 1. So in that case, all I'm doing is being right here. The question is, okay, I pick one person. What's the chance that it lasted longer than 282 days? Okay. So, or more. So right here is 282 or more, longer or more. So it's this area right here. So the first thing I'm going to do is I'm going to turn this 282 into a z-score. 16. Okay, so this is 1. We're now 1 standard deviation away. So now I'm going to make it formal, which is again something that I want you to do. So I am wanting you to draw a picture. Draw this. Find the z-score, part of what I want you to do. And homework or quiz or anything or a test when you're showing your work. Then you're going to write the question down using formal symbols. I'm going to use the probability of what? With my random variable y being greater than 282. Looks like 282 days. As a z-score, it's equivalent. So there's a measurement. Now its equivalent measurement is 1. Remember, using the 68, 95, 99.7 rule, it looks like 282 is exactly at 1 standard deviation. So if I go between -1 and 1, that's 0.68, which means that these two edges right here comprise of together 1 minus 0.68, which is 0.32. The chance of it being greater than 1, which is also all we want right here, that's only going to be half this number. So if I write the whole thing out, 1 minus 0.68 is 0.32, take half of it, and that's that value there, which is 16%. Again, using 68, 95, 99.7 rule, which is an approximation. We want to get a little more precise. Let's use technology. And this technology only goes to 4 decimal places, but it's better. So I'm going to click the greater than button here, and you can see the curve shaded correctly. And I'm going to just enter a 1, positive 1. I see that a more precise value is 0.1587. Using, again, GeoGebra to be exact, but just some kind of technology. So this one did not concern the sampling distribution. This is just as if you were just talking about a normal distribution and you're doing a calculation like before. Let's look at the next question. What is the probability? This one is B, so it follows the first. What's the probability that if we chose 9 hospital records, okay, Now we're choosing 9 hospital records at random. Again, what do I need to know is at random? Unbiased. Okay, that's what I'm really code word for. Okay, assume that this means unbiased. That the average length of a pregnancy is last longer than 282 days. So we're still back to 220 days. That hasn't changed. But what is changing right now? That I'm no longer, this question no longer is a single value like before. So here's my population. Now what am I doing? I'm sampling 9 hospital records. And what am I doing with 9 hospital records? I'm calculating Y bar, the average of the 9. So now I'm doing a distribution that consists of nothing but averages of 9 numbers. What's the center of this distribution? Well, this one's going to be labeled E of X bar, nope, Y bar. Ooh, and what's the value here? That's 266. And why is that? Because I'm assuming that I'm sampling unbiased. Okay, so this is true because sampling is unbiased. Does this value here, the center, depend on my sample size? And the answer is no. Again, remember, this is not dependent on sample size. Sometimes people confuse the central limit with this being equal to this. No, this is something entirely different. This is all about the sampling procedure being unbiased. The central limit theorem only has to do with the shape. Now, if you look at a book, they're going to combine all 3 together. The mean connection, the standard deviation connection, and the shape connection. But the reality is, the shape connection should be by itself. And I encourage my students to think this way because if you don't and get them all confused, you're going to make a mistake. You need to separate each one behaves slightly different from the other. Each one has slightly different criteria than the other. For example, this one is irrelevant of sample size. It doesn't, sample size is irrelevant. All right, so now what about the shape? Well, this one was approximately normal, meaning I could draw this normal shape. So if we already started with a normal one, then the sample size is irrelevant here because this one will be approximately normal no matter what the sample size is. If it's 2, great. If it's 3, again, it's approximate. As a matter of fact, this one will be more normal than this one. This one started already approximately normal, but as the sample size goes up, this one gets closer and closer to normal. So this was already close to normal. So now this was even closer to normal. So this distribution is actually more normal than the original parent population. All right, and so now we're back to the same question. Almost, except what's the difference? This is about the average of 9 numbers. Previous question was about a single value being greater than 282. Now it's about an average of 9 values being greater than 282. We are just going to do what we've always done. Let's find the z-score. 282 minus 266 divided by, but now remember, this population standard deviation is 16. But this is now the averages, same percentage of averages. So now we have to take the 16 and divide that by the square root of my sample size, which is 9. I got this as 16, right? I got 16 divided by, and then square root of 9 is 3. If I do some arithmetic here, I'm going to find that this is right. So now what I'm after is what's the chance that my average of 9 numbers, so now I'm going to write this whole thing out again, what I'm expecting you to do. .282 now is a z-score of 3. Now we are further. 282 is much further away. It's 3 standard deviations. Before 282 was 1 standard deviation. What's happening? Well, remember, as the sample size increases, the variability goes down. But where does it go down to? It's getting closer and closer to the center. In this case, 266 is our center. So all what's happening is the 266 has remained the same position, but this curve is shrinking. The 282 hasn't moved. It's staying still. And as this n goes up, 282 is becoming more and more rare. And if I use 68, 95, 99.7 rule, remember, 3 standard deviations. This is 0.997, and I'm after this area right here. So this must be, using that rule, 0.997, divide this by 2, so I'm all like the little tail. And what does this come out to? 0.0 If 0, 1, 3. What is it we're using technology? Let's come over here and do the same thing. I already have it pointing in the right direction. So I'm going to come over here. Ooh, come on. Put a 3 here. Also 0.0013. Is this unusual? The answer is yes. Double exclamation. Yeah, this is very rare. How rare? What this number says is tenths, hundreds, thousands, 10,000s. So this is 13 over 10,000. So this result, you would get a sample average greater than 282, 13 times out of 10,000 attempts. That's how often you would see on average. So remember, this is just an average, it's a probability. So that's how rare it is. So it doesn't happen very often.